Okay, there's the obligatory shot of lots of people. That's the Blackmagic design booth. As at every NAB, there was stuff at this year's NAB. But everybody has different kinds of stuff that they were interested in. I thought I would show, everyone gives awards. The International Association of Broadcasting Manufacturers, which is basically the trade organization of NAB exhibitors, gives out only 5 awards every year. And they call them the Game Changer Awards. These are the 5 awards they gave out to Bridge Technologies Pocket Probe, which is a stream checker, Mastech Emerald for news, which is for archiving, TC Electronic Loudness Radar, which is for loudness metering. I've shown that on the right there. ISO Videos Viarte for format conversion. And MS Tag Station, which is basically Song ID, was introduced in 2010. Got the award this year. Some other things in the stuff category at NAB. Sonic Notify I thought was very interesting. Little tiny company, and they're trying to do extraordinarily local advertising. I mean, like local, like 3 feet away from you, local. So that's one of their speakers. It emits a 19.5 or 18.5 kilohertz sound. And this would be, say, in the Coca-Cola section of your supermarket. And if you put their app on your cell phone, it leaves the microphone on. When the microphone hears their tone, then it says, hey, you standing in the Coke section, we'll give you 50 cents off on Coke right now. And then IPTEC had radio-controlled vehicle. They are not in the vehicle business. They're in the codec business. They're trying to show low-latency codecs. If you have latency in your codec, then you have a hard time driving the vehicle. Now, up on top of that vehicle, you can barely see there's a couple of cameras. So I've put a yellow circle around one of them, and down at the right, I'm showing you the image of the camera. That's a little tiny camera. That's a camera about the size of the first joint of my thumb. But that is not the smallest camera that you guys are familiar with, because you all have cell phones. And your cell phones probably have cameras, and the cameras in your cell phones are tinier than the nail on my pinky. So Fraunhofer got a brilliant idea. They said, why don't we take the tiny camera out of the cell phone, including the smarts that's associated with it. And they made this Inca camera, and that whole camera is smaller than my top pinky joint. And including its smarts and its wireless transmission, it weighs 2.5 ounces. So they strapped it to an eagle and said to the eagle, go play with your friends. And this was the most wonderful footage that I saw at NAB. It's HD footage, and you can see, who knew before that eagles had lips? And mustaches. Here's another interesting camera that was at the show. It's marrying 2 different acquisition worlds. So on the right side, we have basically an ARRI Alexa. As you can tell from the model number, the Ikegami HDK97 ARRI. ARRI has something to do with the camera. So it's got a Super 35 sensor, ARRI's image processing, and so on. And then the back end of the camera is a standard studio field systemized camera from Ikegami. Kind you would use in a truck or a studio. So great, best of both worlds, except when you want to put lenses on it. So here I'm showing B4 mounts on the left, that's the standard 2/3 inch industry mount, and PL mounts on the right, that's the standard cinematography mount. So on the left, a typical Canon 100:1 lens you might use in sports with a B4 mount. The equivalent in the PL area would be 21 to 2136 millimeters. Well, here's the largest zoom that's available in the PL world. It's the Canon 30 to 300. It's a whopping 10 to 1 zoom, and it's equivalent to 13.1 to 131 in the 2/3 inch world. Down at the bottom, I'm showing a typical Fujinon wide angle for 2/3 inch, 14 by 4.5, the equivalent of 10 to 145. And here I have Fujinon's wide angle lens for a PL mount, wide angle zoom, It's a 14:28. It's not even available yet. It'll be available next year. It's a whopping 2-to-1 zoom ratio and starts at the equivalent of 6.1, so nowhere near as wide as what the 2/3 inch is. So what lenses do you put on that Ikegami Ari camera? And what does that get you? There were 3 exhibits that I thought most improved over the last year, and this is one of them. It's Project Fine from the European Union. This was also at the Futures Park at NAB, and it was there last year too. And there's a few cameras that they have. They'll use 3 to 5 cameras in a small section of a stadium, so less than a 90-degree angle between the cameras. And yet, using their software, they can create a viewpoint for a virtual camera anywhere in the space of the stadium. So you could have a camera looking straight down at the field, just from the information that they've derived from these cameras on the side. You can have a camera that's actually looking back at where these cameras are, even though you don't have a camera over there. And so you're saying to yourself, this is ridiculous. Where did they get the information for that? Well, they're shooting the players as they're playing, and they're turning around, and the computer is keeping that information. They obviously don't have the texture of the field and so on, so it loses texture when it's shooting something that doesn't exist. But for many shots, it's got everything that you need. Now, why do I call it most improved? Last year they were showing this, but the processing was on the order of minutes per frame. This year they were showing it in real time. You could move the camera viewpoint around in real time. More things on improving acquisition. People were talking about higher resolutions, higher frame rates, higher dynamic range. The things in gold I'll talk about a little bit more later. Greater bit depth, higher signal-to-noise ratio, wider color gamut got mentioned, light field capture, and this was one of the sessions at the Technology Summit on Cinema that SMPTE has. It was called Advancing Cameras for Cinema. Just this one session was extraordinary. Wider color gamut, I could not find anyone else anywhere at NAB who cared the least about that anymore. But John Landau was at the Technology Summit on Cinema, and he was asked what's his choice among all these things, and his choice was brighter pixels, whatever that happens to mean. Maybe brighter projection, maybe higher dynamic range, we're not quite sure. But let me go into the concept of light field capture. Here I have a picture of a camera and a lens. The camera happens to be a Blackmagic design digital cinematography camera, but it doesn't matter. The camera can be moved around, so it changes position. The lens can be focused, zoomed. It has iris. It's a certain depth away from whatever you're shooting, and it introduces aberrations. But in front of the lens, we have the light field, and that has everything. That has the possibility of focusing on anything. That has the possibility of zooming into anything. That has the possibility of changing the iris to whatever you want, changing whatever kind of depth of field. And there aren't any aberrations in the light field. So what happens if we could capture the light field? Well, there's 3 different techniques of capturing the light field. On the left is actually a commercial product, the Litro camera, and they use a fly's eye lens between the main shooting lens and the sensor. And the problem with that is it reduces resolution. So they have to start with a really, really high megapixel sensor. But if you start with a really, really high megapixel sensor, then you can't really do video because there's too much information to gather. So commercially available, but stills only. Then Fraunhofer was showing this at their booth at NAB. It's a 6-camera array where the 6 cameras get combined and can capture a light field. And then this was discussed at the Technology Summit on Cinema, an MIT proposal for something called a coded aperture. I'll tell you more about that in a moment. So this was presented in Peter Senton's paper. He's from Grass Valley, but this has nothing to do with Grass Valley. Basically, up at the top left, you see a lens with a typical aperture in it. And then the coded aperture is basically this disc with a pattern of holes drilled in it that you stick into the aperture plane. If you want to get the MIT paper, there's a bit.ly short URL there, /MIT coded aperture, but don't put any spaces in there. And simply by doing that, here we have the ability to change focus. This is done in post-production. We can go from the close focus to the far focus. We can take anything that's out of focus and bring it into focus. Now you're asking yourself, how can you possibly do this? Well, I was talking about the light field in front of the lens. At the aperture plane, we pretty much have most of that same light field. It's going through the aperture plane before it hits the imager. But the problem is we don't know what that light field was. We don't have any way of reconstructing it. By putting that disc in that has holes drilled in it, the parts that don't have holes drilled in it are putting zeros into the light field. Zeros that don't exist naturally. So you can search mathematically for where those zeros are, and then you can reconstruct the light field that existed at the aperture plane. Pretty amazing. And then here's the Fraunhofer on the right. Take a look at the right edge of the chair relative to that box behind it, or printer, whatever it is. And you can see you can even change position in post. So now in post, you can do tremendous numbers of things that you weren't able to do previously. Unfortunately, like the Grass Valley Viper when it first came out, you have the same problem of it doesn't look that good live. But in post, you can do all kinds of stuff.
Is that storing some data somewhere that you then...
No, it's not storing any data. Basically, you're just getting what goes through that aperture and goes onto the sensor, and it's the same as you would normally get out of that sensor.
How do you modify it in post?
You get to find where the zeros were in the light field based on the coding of the aperture, and then you can reconstruct the light field, and having reconstructed the light field, you can then reconstruct focus or anything else that you want to do.
There's a computational process.
There's a big computational process,
there's
right?
Not metadata that's carried.
No, there's no metadata. But you can derive all kinds of things. You can derive depth information, so you can do 3D in post for something that you shot in 2D. You can derive depth planes if you want to have graphics flying in front of somebody and behind their head or something. That can be done from this coded aperture. But let me point out an interesting thing after I show you the next thing. Did you have a question, Dave?
Is it sort of like a 2D storage or a hologram? Digital storage.
A hologram also captures a light field, but a hologram captures more of a light field. So you're limited. You are doing it in the aperture plane, so you're not doing it in front of the lens. You're not getting everything, but you are getting a substantial amount of information. But this picture, some of you may remember, this was also shown at that same session at the Technology Summit on Cinema. The only light in this picture is coming from the lamp that is aimed directly at the camera, and yet even with this projector and this lighting condition, you can see every chip on the chip chart. So there is a 10 million to 1 contrast ratio in this image, more than 23 stops, and I've zoomed in on the filament of the lamp here just so you can see that you're seeing every coil of the filament. You are getting a full more than 23 stops of information. Now this picture, those of you who remember it, might remember I showed it to you when I talked about NAB in 2008, 5 years ago. This is a Grass Valley development. This is in the Grass Valley Sensium sensor, and yet it has not yet been implemented in any Grass Valley product. It has been implemented in another company's product that uses the Sensium sensor, which is Lux Media Plan, the German company. But Grass Valley has not implemented it. So just because stuff can be available doesn't mean it's going to be available. The coded aperture paper that I showed you from MIT, that was delivered in 2007. Some more on computational imaging. On the left, we see at the top a good picture, at the bottom a kind of blurry picture. It's blurry because of chromatic aberration. And one of the reasons that lenses cost a lot, and I'll talk about a very expensive lens later, is that they try to eliminate the aberrations in the lens or reduce them tremendously. Well, we already have cameras that can deal with lateral chromatic aberration and change that, fix it. So what can we do if we have even more computation? Well, there was a guy on the camera panel, Eric Fossum. Some of you may know who he is. For those of you who don't, I'll give you a very brief bio. He's the inventor of the CMOS sensor. So what you have in your cell phone, what you have in your point-and-shoot camera, what you may even have in the cameras you're using in your studio or in the field. He invented that. Now he's moved on to a different kind of sensor. He calls it the quanta image sensor. And one of the people on the panel was from NHK talking about the 8K camera that Lynn was talking about earlier. The 8K camera has 33 million pixels. What Eric Fossum said was in the space of one of those 33 million pixels, he'll have about 250 across to 250 down jots, which is what he calls his sensors. So there's maybe 100 billion sensors or photo sites on his quanta image sensor. And they act like film grain. They're either exposed or not. That would be true digital imaging. Today we have sampled imaging, but it's still analog. And the sensor could be read maybe 1,000 times a second. So coming out of that sensor, we have 100 terabits per second of information. A tremendous amount of information. Obviously, we're going to have to do a whole bunch of stuff before that comes out into a product, but hey, this is the guy who came out with this sensor, so he does have cred. This is one of the cameras that was introduced at NAB. It's Blackmagic's designs pocket digital cinematography camera for $995. That's the size of a standard point-and-shoot pocket camera. But it is a true digital cinematography camera. It allows you to change shutter angle and interchange lenses, do all kinds of stuff. Just for reference, at the top I put Blackmagic Design's audio monitor that they also introduced this year. It's $1,500. So the audio monitor is 50% more expensive than the digital cinematography camera. Was that the smallest digital cinematography camera at the show? No. There is the Novo camera made by View Factor Studios based on the GoPro Hero 3. Radiant Images has it in the United States for rental only. Comes with interchangeable lenses, back focus control, the usual digital cinematography things, but that's the size of the camera. And what do you put the cameras on? This was a mount from Firefly Systems, the Movie M10 mount. Everyone who touched this thought it was the most wonderful handheld mount ever. It's about $15,000. So you take your $1,000 camera and you stick it on a $15,000 mount. A little bit more from the SMPTE Technology Summit on Cinema. We start with a joke, perhaps. An anesthesiologist, a neurosurgeon, and an ophthalmologist walk into an imaging conference. That was actually the case. They were all at the conference. The reason for the anesthesiologist is anesthesiologists know how to make people lose consciousness. So they figured that he knows something about consciousness and could talk about that relative to frame rate. But this is from the presentation of Christopher Pack, who is a professor of neurosurgery, and he's showing some reactions of the brain here to different frame rates. So some of the reactions that people had to The Hobbit may be something that's innate in us, or maybe it's something we're still evolving. The jury is still out on this. Some concerns that were expressed at the show. White space transmissions, everyone's been concerned about that for a while, but at the Futures Park, NIC, the Japanese National Institute of Information and Communications Technologies, was showing cognitive radio per IEEE 802.22 and IEEE 0.11 AF. So they were doing transmissions in white spaces that supposedly will not interfere with anybody. Then, as Lynn mentioned, HEVC, the high efficiency video codec, H.265. I did not hear a single technical concern from anyone. As far as everyone's concerned, this is a magnificent, wonderful new codec. And Lynn was talking about the NHK transmission of 8K in 2 television channels with 2 polarizations using 180 megabits per second. At the Fraunhofer booth, they were showing HEVC 4K at 5 megabits per second. So worst case, if it took 4 times 4K to make 8K, that would be 20 megabits per second, which just about fits into a US standard television channel. But worst case is probably not going to be the case because energy goes down as detail gets finer. So maybe we're talking 8 megabits per second or something for HEVC using the Fraunhofer stuff. So definitely 8K can be transmitted in a US broadcast channel. And in fact, based on what Fraunhofer was showing, you could have a 4K multicast in a US television channel. But there were concerns about rights. Now, not so many concerns about rights in terms of the professional world because you buy an encoder, if something comes up and the encoder costs $1,000 more, okay, fine, you pay an extra $1,000 for the encoder. But on the consumer end, you don't pay an extra $1,000 per decoder. That's a big problem. So people want to make sure that the rights issues are nailed down on H.264. And then we had Ethernet AVB. AVB is for audio-video bridging. That's IEEE 802.1 AS. The idea is to replace all non-IP cabling in a broadcast or video facility. So no more HDSDI, no more HDMI, no more AES-3, just standard IP cabling. And the timing is supposed to be sufficient to allow video dissolves. But is it? And one question on this is there's another IEEE standard, 1588, about precision timing, and not all Ethernet plants are 1588 capable. But here's the idea of the IEEE 802.1 AS, the AVB, how you would get timing. It's like Genlock, except it's like two-way Genlock. So it figures out how long your cable length is, it automatically adjusts for you, and so on. Here's one of the issues associated with it. The two blue areas, you could do connections that would allow a video dissolve, but in the green areas you couldn't do that. And here is a list of the people associated with the industry group for AV bridging. It's called the AVNU group. And you'll see a lot of familiar names here, but they're primarily audio names. And this is because AES has been dealing with this issue longer than SMPTE has. And there was some concern that maybe the standard is not quite good enough for allowing a dissolve. Other people say, with the equipment today, it doesn't matter. You can be a half a line off and still do a dissolve. So there are different points of view about this. Another interesting interconnect thing at the show, many booths talking about SFPs. These are small form factor pluggable transceivers, primarily used now in rack mount equipment. You can plug in a fiber connection or a coax connection or an Ethernet connection or an HDMI connection, whatever it is that it seems that you need. But very interesting thing, Embryonics at the show was showing a little handheld 2-slot device, so you could do conversions in the field just by taking 2 SFPs of whatever nature you wanted, plugging them into the device. And Barnfind was showing a frame, a 1-rack unit, 16-hole frame, basically, again, signal neutral, so you can plug in whatever SFPs you want and make whatever connections you want. Most improved number 2, the Sony PVM 2541A. Now, last year, Sony introduced the PVM 2541, which is a 25-inch OLED monitor. Looks very good and fairly cheap, much cheaper than any of the CRT monitors that were out there for that kind of quality. But there was a problem. If you used it for video control, then you have one video operator's got a monitor right in front of them. Next video operator's over here. The senior video operator sets something up and says, okay, make it look like mine. And the other guy is looking way off axis and is seeing a big hue shift. So this year, you see on the right there, there's a 2541A on top. On the bottom is a 2541A, and below that is a turntable. So you could swing those around, and the hue on the bottom one would change, the hue on the top one would not. Tremendous improvement from Sony, and no big price problem for that. Lynn was talking before that the best that Cisco could do was 42-inch panels butted up against each other. Well, here is a 4K display from Layard, and it's, I think, 23 feet long. It's using surface mount LEDs, and the LEDs are full color in each of the surface mount devices, and there is a true 1.9 millimeter pixel pitch between the devices. So if you stand at a normal TV viewing distance, say 9 feet away from this thing, you cannot see the pixel structure. So this is your stadium LED video wall except for your home. But not at home prices yet. And just in case you want to stand closer than normal TV viewing devices, one of their competitors, Silicon Core Technology, was showing panels with a 1.5 millimeter pixel pitch. Again, between full-color surface-mount devices. Down at the bottom, I have a Christie projector. It's 35,000 center lumens, but only a 750-hour lamp life, weighs 251 pounds, costs $161,000, but it can do 60 frame per second 4K. At the top was an NEC laser projection prototype demonstrated at the SMPTE Technology Summit on Cinema. Again, 4K, quality, okay. You know, nothing you want to write home about and say it's the most spectacular thing I ever saw, but okay. And it's just a prototype, it's only going to get better from there. A little bit more from the SMPTE Technology Summit on Cinema. When we're talking laser projection, ooh, lasers, what happens if people turn around and stare into the projection booth? So this is why the ophthalmologist was there. And he said, basically, if you stare into the projection booth and you see a xenon light, you're in much worse shape than if you see a laser. So they were expecting that very soon the FDA is going to approve laser projection and say that it's not any special category or anything, no worse than xenon projection. So you may remember this from 3 years ago. This is the elephant in the room. 3 years ago, the elephant in the room was 3D. Every booth at NAB was talking about 3D. And this brings me to my third of three most improved, and that's Dolby 3D, which means a different thing now than it did several years ago. Several years ago, Dolby 3D meant the interference filter glasses. Now Dolby 3D means glasses-free autostereoscopic viewing. Last year, it was not a comfortable thing to look at. This year, it was a very comfortable thing to look at. Very nice, very pleasant. Would I pay money for it? I don't know. But it was pleasant. And now, thanks to Lynn and everyone else at NAB, I'm going to be able to demonstrate to you, without glasses, on this very screen, 3D. So here we have an image from the Life of Pi, and now you are going to see that fish jump right out of the frame. Oops, back up, show you that again. See it? Jumping right out of the frame? Okay, first time I saw that, I thought, wow, you know, these Dolby guys came up with a really great gimmick here. And so I asked them about it, and they said, no, that's in the movie. And Ang Lee, the director, came up with this brilliant idea, which was he would cheat up a letterbox bar just so he could do that in this scene. And then the next camera cut, the letterbox bar went away. So this year's elephant in the room was Ultra HD, 4K. And thanks to Ed Grogan, some of the things that were listed as being for 4K, 4K capable were tower lights, microphone markers. Everybody was 4K capable. No, just 4K. But there were some interesting 4K developments. In cameras, you could get a Blackmagic design 4K camera, basically the same digital cinematography camera they showed last year, but with a different sensor, for $39.95. In storage, last year, Red was talking about Red Ray, and it's $17.50. You go, wow, that's an amazing price for a 4K player. So Sony came out with the FMP X1 that's $6.99, and there's 10 movies preloaded on it. Processing, Blackmagic Design had a production switcher for $19.95, a 4K production switcher. Now, this doesn't include the control surfaces, but it uses the same control surfaces as their older switchers. Distribution, again, Fraunhofer showing 4K HEVC in just 5 megabits per second. Displays, Sony showed the XBR 55X900A, that's the thing on top there, 55-inch 4K display for less than $5,000 retail. But I do have to point out with the asterisk down at the bottom there, the HD version of the same display with the same technology, which is quantum dot technology, is just $2,800. There were several 30-inch professional monitors, kind of a strange size, but maybe something you would use for looking at video in 4K. And, of course, we have the 9-inch 4K monitor from Astro Design, which is a true 4K monitor.
4K panel.
A 4K panel, yeah. Panasonic's been showing a 22-inch 4K tablet, but Astro went even smaller. Now, Marshall Electronics had this interesting 4K monitor. It's called the 2K 4K monitor. And if you look at the resolution, it's 2560, which is a little more than 2K, by 1440. So what makes it 4K? Well, you can zoom in on things to see what's going on. But what kind of connections? There's 4 BNCs times 2 here. 2 of them are outputs, 2 of them are inputs in each of the sets of 4. But what do you put on that? And I'll get into that a little bit more in a moment. Now, one reason that shooting 4K matters, the bottom scale here is just arbitrary numbers, but if number 11 happens to be 1920 pixels, then sampling theory says you got to do some kind of a roofing filter, and if that's 1920 pixels, then the contrast ratio at 1920 is 0, and 0 is just gray, not very good. But if that's 3840, a typical 4K kind of number, then the contrast at 1920 pixels is 64%. So we can tremendously improve HD pictures simply by shooting them with a 4K camera. We can also zoom in. There are other possibilities. We can change the framing. We can do image stabilization without losing anything. So there's lots of good reasons why we should shoot 4K already, and both CBS and Fox have been doing that in sports. CBS zoomed in the Super Bowl using a 4K camera. Fox has been doing similar stuff.
I recall the same thing when HD came out, that you
Yeah,
could
exactly.
SD by shooting with an HD camera.
Correct. Another possibility, if you're still interested in 3D, you can do 3D side by side with a 4K camera. And if you have a 4K display, you can do passive glasses 3D with alternate line eye views. And Sony was showing that at IBC, and it was actually quite nice looking. But other than those things, we have a few concerns. One is lenses. I was mentioning before cost of lenses. Well, here's Fuji's 3:1 zoom 4K lens. It's $100,000 list price. So you take the $100,000 lens and you stick it on the $4,000 camera until we get something going with the computational imaging. And also that's a 3:1 zoom.
Do you get a situation at some point where the mounts are not stable enough to keep the lens sturdy, or is that
I don't think that's an issue.
mechanically?
They seem to be good. But connections also, here's the back of that Blackmagic Design 4K switcher that I was mentioning, and it's got 6 inputs, and they say they're 6G SDI. Wow, great, wonderful. We'll do 4K on that, except you can't. If you work out the numbers for 4K at just 8 bits per pixel at 60 frames per second, it turns out you need an absolute minimum of 8K. You can't do it in 8G. You can't do it in 6G. So 6G you can do with 30 frames per second or 24 frames per second, but not 60. And then there's the issue of formats and visibility. So formats, why are we calling 4K Ultra HD rather than 4K? And it's an issue of lawsuits, because so much of 4K is actually quad HD, so it's twice HD horizontally, twice HD vertically. As Lynn pointed out for the 8K, he said, so-called 8K or supposedly 8K, 3840 is less than 4K. So people were concerned that some state's attorney general is going to say, no, that's not a 4K device. So that's why they're not calling them 4K devices, they're calling them Ultra HD. Then there's issues of the frame rates. 8K has variations too. Red already had a 5K device at the show. They were upgrading people's cameras to 6K devices. Here, by the way, were some 8K cameras that were shown at the show. Hitachi had this ENG EFP profile 8K camera, so very impressive, like a standard camera, except Astro had a much smaller 8K camera. And then there's this question of single sensor optical filtering. So this was shown by Peter Sentin at that Technology Summit on Cinema camera panel. There's a zone plate, and here in the blue you can see from a single sensor camera there's extra aliases. Same thing in the red, there's extra aliases, but in the green we have very little or almost none of those aliases, and that's because the green has twice as many photosites as the red or the blue. But you can only optically filter for one of them if it's a single sensor. You can't optically filter for both sizes. So anti-aliasing is a problem. How about visual acuity? Some people say, well, you can't see 4K at home. There's a standard eye chart on the left. The E that's shown here is not the E from the top, but the E from the 2020 line. It subtends a visual angle of 5 arc minutes. And every portion of it subtends an angle of 1 arc minute. And since there are 2 lines to a cycle, a white line and a black line, then 1 arc minute translates to 30 cycles per degree. And if you sit 9 feet away from your television set, which is typical based on the sizes of living rooms, then a 25-inch 4x3 TV is 15 inches high, and that's basically all the resolution that you can see, 480 lines on a 25-inch screen. If you have 1080 line HD, then you're supposed to sit 3.2 times the height instead of 7.2 times the height, which would mean that you would only see full resolution from a 1080 line HD if you had a 70-inch screen at home, basically. So does 4K mean that we need to have a 140-inch screen at home? Here's a conference I was at a couple of weeks ago in London. A guy from the Imperial War Museum said, "These people are insane. We've got to stop them," talking about 4K in the home. But let me point out that on that eye chart, there are 3 lines below 2020. So 2020 may be called normal vision or perfect vision, but when NHK did its most recent testing, they tested the people who were going to be doing the evaluation, and they found that 2010 was more common for them, some of them 27 even. Another is that E has really sharp edges on it with high contrast. This is what the E would look like if I was showing a true 30 cycles per degree. So to get sharp edges, you need to add odd harmonics, and odd harmonics add up to higher frequencies. And whatever the home viewing distance is, let's say it's 9 feet, then we have a relaxed viewer who might be 9 feet away, and then an edge of the seat viewer. And that green stick that you see there is a yardstick. So there's about a 3-foot difference in viewing distance, just depending on the way somebody wants to watch. And whatever people do at home, when they go TV shopping, they're standing 1 foot away from the screen. So they will certainly be able to see a 4K difference when they're shopping for their TVs. Here we see some EBU testing that was done recently, and the scale at the bottom is 720p, 1080i, 1080p, and UHD1, which is 4K. And the red line is standard home viewing distance, 2.7 meters, and the black line is 1.5 picture heights away from the screen. And basically we can see about a half of a grade of improvement at 1.5 picture heights, but even about a third of a grade of improvement, pretty significant at standard viewing distances. So unquestionably, people can see 4K at home on a reasonable size thing. This was a 56-inch screen. So yeah, they're not going to see it on a 25-inch screen, but 56 inches certainly. Will they pay for it? Is it that dramatic a difference? That's a different kind of question. So the 4K bottom line. 4K acquisition, useful but limited in lenses and connections. 4K is visible, at least for some viewers' screen sizes and viewing distances, but 4K is manufacturer driven. There are no consumers that I know of who are saying, "Oh, if only I had more resolution on my TV." 4K at 60 frames per second is 8 times the pixels per second of 1080i at 60 frames per second. For 422, that would be 8 gigabits per second, bare minimum. 4K costs more than HD, even at the cheap stuff. And whatever happened to 1080p at 60, which was supposed to eliminate interlace artifacts and do all kinds of improvements for us?
And everybody's TV's been able to show it for years.
Yeah. So that's my NAB.